Welcome back to the Laser Grid Laboratory. In Episode 2, we built triangles using 3 specific side lengths. Today, we want to know how to perfectly construct a triangle when we are given exact angle measurements instead. This diagram shows our first method, the side angle side, or SAS construction. We start by drawing a 5 centimeter baseline. Then we use a digital protractor to project a ray at exactly 45 degrees. Finally, we measure exactly 4 centimeters along that ray to lock in point C. Now look at the ASA, or angle side angle construction. Instead of measuring a second side, we project 2 specific angles from our known 5 centimeter base. We shoot one laser ray up at 45 degrees from the left and another at 80 degrees from the right. Where these 2 rays cross in space forms our third vertex. As long as you meet these specific angle and side conditions, the geometry is locked. The intersection of those lines dictates that there is exactly one possible shape that triangle can take. That raises a question. Can we use any 2 arbitrary angles for an ASA construction? Or is there a point where a triangle physically cannot exist? Let's run a visual test to find the boundary. We'll start with a horizontal baseline. From the left, a ray shoots up at 40 degrees. From the right side, we sweep a second ray inward at 50 degrees. Because both rays lean inward, they cross easily. Watch the right ray as we sweep it wider. At 90 degrees, the intersection pushes higher. But when it hits exactly 140 degrees, the 2 rays snap into parallel alignment. They will shoot off into infinity without ever meeting. When interior angles on the same side add up to exactly 180 degrees, the lines become parallel. Since parallel lines never intersect, a triangle exists only if the sum of any 2 angles is strictly less than 180 degrees. We can calculate these limits, but proving the exact sum of a triangle's interior angles without measuring them requires a different approach. Ancient Greek mathematician Euclid solved this using the logic of parallel lines. Look at this triangle with base angles of 50 and 70 degrees. Euclid's first step was to draw a single dashed line straight through the top vertex, positioned perfectly parallel to the base. With that parallel line in place, the left side of the triangle acts as a transversal. This forces the top alternate interior angle to also be 50 degrees. On the right side, the same rule applies. The opposite alternate interior angle must be 70 degrees. The original top angle is now flanked by the 50 degree and 70 degree angles. All 3 sit on a single flat line. This proves the interior angles of any triangle in the universe must perfectly form a straight 180 degree line. This diagram shows what happens when we extend the triangle's baseline. It creates an exterior angle, shown here in neon magenta. Let's set our interior angles to 50 degrees and 60 degrees. Pause the video here and use the 180 degree rules we just learned to find the value of that magenta angle. First, the missing third interior angle must be 70 degrees. Since that interior angle and the exterior angle sit on a straight line, they subtract from 180 to give us 110 degrees. Look at the relationship between the numbers. The exterior angle of 110 degrees is exactly equal to the sum of the 2 opposite interior angles, 50 plus 60. This pattern repeats for every triangle you encounter. Our holographic chalkboard brings today's rules together. You have a triangle with a top angle of 50 degrees and 2 equal base angles, B and C. Your goal is to determine the exact degree measure of angle B and the exterior angle ACD. Calculate the base angles using the angle sum property first, then apply the exterior angle rule to find the final degree measure. Today, we constructed triangles from precision angles, defined the parallel limits of geometry, verified Euclid's 180-degree proof, and identified the exterior angle relationship. Drop your answer in the comments, and we'll see you in episode 4, where we drop altitudes to solve the spider box riddle.